thank you very much for the opportunity to speak at this very nice seminar series and for the very kind introduction. Yeah, so today I'm going to tell you about a kind of series of work that I've been doing over the last couple years in trying to bridge the gap between some recent developments on the more formal side, in particular what goes into the name of conformal colliders, and the real world colliders such as the LHC that most people here are maybe more in tune with. And so this work will rely extremely heavily on the use, both philosophically and technically, of effective field theory ways of thinking, both in the ways that one kind of makes these conformal collider techniques actually meet the LHC, and also in the way that we're going to try and think about jets using the operator product expansion, which is kind of one of the cornerstones of effective field theories. And so throughout this talk, I'm going to try and stay at a relatively high level because I think there's quite a diverse interest in the audience, and to just kind of give an overall flavor of this program. But of course, people can ask more technical questions at the end if they want. And so I should say this is work done in collaboration with a large number of people over quite some time. And so in particular, I just want to highlight Hao Chen, who's an exceptional student, and Hua Jing, who we've been kind of working on this for a number of years. And then I'll highlight a number of other authors shown here as we go throughout the talk, and I'll show different kind of features of this work. So just to get things kind of started, so at these big collider experiments, when you collide things, what you get out are these incredible sprays of particles, which are kind of going everywhere, of QCD particles. And in particular, they're collimated in sprays, which are called jets. And so the kind of classic way of thinking about these was essentially in terms of cones going in particular directions. So they kind of have an overall energy and some general directions. And so this is kind of work building on the original seminal introduction of these jets by Sturman and Weinberg, but it's being kind of refined into a precision science for the LHC. And so one can make very robust predictions for these jet cross sections and also use them in almost every analysis that goes on at the LHC. And so in the last maybe 10 years or so, there's been a kind of transition from trying to, or from talking about jets as cones of energy, where you don't really care what's going on inside them, to trying to understand in more detail the statistical structure of the energy flow within the jets themselves. So that's kind of illustrated here with this 3-particle correlator. So you could measure, for example, how energy is correlated in the jet. And that's a much more kind of detailed question about the structure of, in this case, QCD, as compared to these more basic jet cross sections where this jet is just kind of a blob. And so you can ask, why would you want to do this? And so the reason why this was originally kind of brought to the forefront, and so this is something called jet substructure. And so this uses the internal structure of jets to provide new ways to study physics at the LHC. So since the experimentalists just see the kind of spray of energy at infinity, if you want to understand what's going on internally at the microscopic level, for example, if you produced some new particle, one of the ways you can do this is to study in detail the structure of the energy flow and to identify cases where it looks different from QCD. And so I'm not going to get into the technical details of these searches, but this is kind of a very obviously powerful thing if you can do it. And this kind of idea, which was proposed around 2008 by these particular authors here, kind of reinvigorated the study of jets in QCD as an object of kind of real interest in themselves, because if you can understand them, then it opens up huge new avenues for searching for new physics at the LHC. And so just to show that this is not kind of a one-off thing, but a very general technique, you can use it to search for essentially whatever your favorite microscopic physics is. And it's had a huge impact on searches at the LHC. And so these are just some various pictures of using these energy patterns at infinity to identify the underlying physics of the collision. However, the LHC is kind of a really remarkable machine with these extremely high energies, and one would like to kind of fully take advantage of this and transition from these kind of tools for tagging or identifying the underlying physics to real first principles theoretical calculations where you can really probe or fully exploit this remarkable LHC to probe the kind of structure of quantum chromodynamics and the standard model at these previously inaccessible energies. And so, of course, in these very, very nice events, you have many interesting opportunities to study QCD in particular and quantum field theory more generally at these very high energies, as well as to make precision measurements, for example, of the strong coupling constant, which determines the internal structure of the energy flow, or parameters such as the top quark mass, where you can have this top quark decaying into your jet. However, to really perform this type of calculations and really gain a precision understanding of detailed questions such as these correlation functions in this extremely complicated environment of the LHC really requires the development both at a technical level of new sets of theoretical tools to be able to actually at a technical level do the calculation, and maybe more generally just new ways of thinking about jets, and in particular trying to understand what the kind of actual questions you want to ask are, which allow you to make contact with the underlying field theory. And so I think it's really in this side that I'll try and highlight in this talk, a kind of very complementary perspective to jets coming from the more formal perspective, where one has to really sit down and think about what one is actually doing at a deeper quantum field theory level when one is measuring jets at the LHC. Okay, so from a QFT perspective, if you're kind of a formal theorist, what are you actually doing when you're studying jet substructure? And so from a field theory perspective, what you're doing are you're studying matrix elements of what are called, depending on your background, energy flow or ANEC or light ray operators. And so these are essentially an operator definition of a calorimeter cell in an experimentalist detector. And so these actually have a very simple definition, which are shown here, or it's kind of very intuitive. Namely, you take your stress energy tensor, you move it out in some particular direction, you integrate over all time because the flux of the particles will just come in through all time, and then you move it off to infinity because that's where the experimentalists have their detector. And you can either think of this very concretely as a detector cell, as shown here, or if you want to show the fact that this is some form of non-local light ray operator, you can show it in this kind of Penrose diagram here, which shows this integration over time. And then you can use these operators to define the jet substructure is essentially the study of the correlation functions of these objects in some particular state, for example, the state produced at the LHC. And so if you had all these correlation functions, they would completely characterize the flow of energy or any other charge you wanted at asymptotic infinity. And so the very nice thing about this is that these are a form of correlation functions which you can study using all the standard techniques such as symmetries and an operator product expansion, as I'll show. And so it's a kind of very nice way of formalizing what you actually want to study in jet substructure. And so since these are maybe a little bit unfamiliar to people, I just kind of want to put them into the context of other observables in quantum field theory. So these energy correlators kind of take an interesting intermediate role between amplitudes, which everyone is familiar with, and correlation functions of local operators, which everyone is also familiar with. And so the reason people in collider physics are, of course, interested in amplitudes is that they involve asymptotic states. And so this is what you need in collider experiments. But unfortunately, they are not IR finite, which is why one has to, for example, make or use jet algorithms to define infrared safe observables. On the other hand, correlation functions are the kind of standard observable which one uses in condensed matter experiments. And so these are, by construction, either you can call them IR finite or non-perturbatively well-defined, but they are not what one commonly uses or what one uses at all in collider experiments because they don't involve asymptotic states. And so these energy correlators are kind of a hybrid of an amplitude and a correlation function. And that's extremely nice because we'll be able to use techniques from both of these areas to understand these objects. And despite their physical kind of importance or their central role, as I'll hopefully convince you in the study of jets, they're much less explored than their amplitude or correlation function counterparts. But this is starting to change due to a large amount of work from a number of different directions. And so I personally think these energy correlators are sufficiently interesting just in and of themselves as objects, but it becomes even more interesting at the LHC, and in particular for jet substructure, because you're generally interested, or in jet substructure, you're interested in the case where all of these energy correlators are brought together at very small angles. So you're not in a generic configuration, you're in what's called the small angle or operator product expansion limit. And so generically in quantum field theory, as you bring operators together, you expect to see some form of universal behavior. And so for local operators, this is governed by the local OPE. And so it turns out, as was originally argued by these authors here, and as I'll discuss in more detail, remarkably, these calorimeter cells actually obey an operator product expansion shown here, where you can expand products of calorimeter cells over another class of operator, which can essentially be thought as some generalized form of calorimeter cell. And so this is a natural kind of generalization of the local OPE. And so the very beautiful feature of this is that it predicts, much like the local OPE, the scaling behavior as these calorimeter cells are brought together. And Hoffman and Maldacena, in their original work, argued not only that these satisfy an OPE, but that one can just talk generically about energy flow in jets by studying the symmetry properties and the OPE structure of these light ray operators. So you can, instead of doing calculations in terms of quarks and gluons and all that type of stuff, you can just study them from a more formal perspective by studying the operator product structure, which lives on your detector at infinity. And so this all sounds extremely beautiful, but and so this was proposed in about 2009. But there's this kind of nice exchange shown here at the KTP, and this is real wordings of these people taken from a video. And so Polchinski asked, well, this is a kind of very nice picture here, but of course there's a huge amount of QCD data, and can you see this scaling behavior, for example, predicted by the OPE? And then Maldacena's response was, people do not do this. I haven't figured out why they don't. I think they just haven't thought about doing it in this way. And so this was certainly true at the time, and even now, 10 years later, no correlator or none of these correlators have ever actually been measured at the LHC. And so there's been kind of a disconnect between what has been going on in jet substructure measurements and all these beautiful theory developments in the more formal world. And so I should just say that, I mean, there are some exceptions to this general statement, which I made here, in particular, these people shown here. And so my apologies to them that I'm giving a very kind of broad brush overview of the history, but yeah, their names are here. And so it's worth understanding just a little bit why this kind of approach was not adopted. And so one of the reasons is that the classic approach to studying jets, which was introduced in kind of the mid-70s, was before our understanding of quantum field theory at the level which is required to really understand it in terms of these light ray operators. And so in particular, the classic approach to studying jets is to use kind of jet shapes, which can be thought of, I mean, most people here are probably familiar with this very famous thrust observable, which is essentially kind of measuring the spread of radiation about some particular axis. And so these were invented in the kind of very early days, where the goal was to study the kind of underlying S matrix element. And so these observables like thrust are kind of just an infrared and collinear safe proxy for the underlying partonic collision. So for example, in this case, right, this is just some proxy for a QQ bar state. And then you could have a 3-jet resolution variable, which would be a proxy for the quark-quark gluon state. And you can study, for example, how they depend on the angles and check that this agrees with the underlying theory, which at that time was trying to be worked out. But now that we have a very detailed understanding, the goal is no longer to study the underlying hard matrix element, but rather to study the actual distribution of energy within the jets. And so for this one actually wants to ask a very different type of question. But the kind of historical prejudice of framing it in this way was extremely strong. And then the second point is that these were actually proposed, in particular, the 2-point correlator was proposed very early on by this group of people here. And so depending on your perspective, whether it's positive or negative, QCD is not a conformal theory. And so in particular, at the energy scales of the of LEP, which was the collider which was around at the time, hadronization effects have a very large impact. And so in particular, this is just kind of an illustration of a simulation on hadrons and partons in this small angle regime. And so you can see that you have very large corrections in this region from hadronization to the structure of energy flow. And also, if you look at these kind of jets, they have 3 or 4 particles per jet. And so if you want to measure something like a 5-point correlator, it will behave very differently than in a conformal theory, just because the phase space is actually limited by the mass of the individual pions that are being produced. And so it's very far away from this high energy limit where QCD behaves as an asymptotically free theory. And so this is where the kind of LHC really kind of comes in and gives us kind of a spectacular opportunity to completely rethink the way we study jets. And so here we have these extremely high energy jets, say at the scale of 1 TeV, instead of the 50 GeV jets at LEP. And they also have many, many particles. And so one can really start to study actually their statistical properties and understand these from first principles calculations. And so what I want to talk about in this talk is some progress in our understanding of jet substructure, which will allow us to directly measure these correlation functions, which I've discussed, and really study their associated light ray OPE scaling and the actual shape dependence of these multi-point correlators. And so the thing that's kind of very nice about this for me is it allows one to formulate jets, even in this complicated environment, in a way that's much more similar to the way that one talks about kind of critical phenomena or condensed matter systems. And so we'll be able to, just like for the local OPE, you can measure correlation functions. So this is just some plot in the Ising model, or scaling behavior near a critical point. Here we'll also be able to see beautiful scaling behavior associated with this operator product expansion and actual shape dependence of these multi-point correlators which are living on the detector. And so not only does this give us kind of new ways of looking at jets and understanding QCD, but it also really allows an opportunity for interplay with all these nice developments on the conformal field theory side. And so we'll have a lot more tools with which to perform concrete calculations. And so just as an overview of the topics, and I may, depending on my time, have to skip a few. But so I'm going to first try and go through this most basic property, which is the scaling behavior, which is governed by the operator product expansion, and show that one can really just beautifully see this in real world LHC data like this, and that you can really start to think about jet observables as just scaling phenomena and put it into the more general framework. Then I'll go beyond that and look at the structure of these multi-point correlators, in particular the 3-point correlator shown here, and show that one can start to look at kind of non-Gaussianities in the interactions of quarks and gluons. Then very briefly, I'll just show how one can use this to probe the kind of hadronization transition from these asymptotically free quarks and gluons to just free hadrons propagating out into your detector. And then depending on the time, I'll maybe briefly have a chance to discuss how one can use these to perform, for example, precision standard model measurements of the top quark mass, which will imprint itself into the structure of these correlators. Okay, and just as a quick aside, so throughout this talk, I'll actually show real data from the LHC. And so the way that I'll be able to do this is using this CMS open data, which has been packaged into this MIT open data for us by Jesse Thaler and Patrick Komisky. And so this is data which is perfect for jet studies because jets are produced in every event. And in particular, it's very nice for rapid testing of new theory ideas. So you can see that the way that this works is one can ask at kind of like 2 p.m. in the afternoon if one can get this, and then one can have plots by 10 p.m. at night. And so this is obviously a very positive thing because it allows one to test things, but it should also be taken with kind of a grain of salt because in this, a proper experimental analysis, for example, involving unfolding and all the details, cannot be done in one afternoon. But this is meant to kind of motivate that these things behave in a very interesting way, and it can then be done more carefully by professionals, i.e. experimentalists. And so things like error bars that I show should not be taken seriously. This is just meant to kind of show that these things have a very nice behavior. Okay, so scaling behavior in jet substructure. So the operator product expansion is kind of a cornerstone of the way of thinking about effective field theories. And this allows one to study things in the Euclidean regime, so something like DIS. And in particular, what it does is as you bring two operators together, it tells you a universal scaling as a function of that separation. And so in particular, it shows that QFTs, even depending on all the other messy details, typically exhibit universal behavior as these operators are brought together. And so what this light ray operator product expansion does is to allow one to talk about these detector cells in exactly the same way. And so in conformal field theories, this light ray OPE is actually proven to be a convergent and rigorous expansion. And it's just kind of written in a very schematic way shown here, where you expand in the angle between the detectors, and the expansion is just like for standard Lorentzian observables in the twist of the light ray operator. And so here, I'm just gonna focus on the leading behavior, which is what will dominate in an actual kind of plot that one sees for the LHC. And therefore, to understand what appears in this operator product expansion, and to understand the scaling behavior in jets, one has to understand the twist two light ray operators that appear in the particular case of QCD, because these are what are going to appear as you perform this operator product expansion, or at least those are what will dominate the scaling behavior. And so, of course, the local twist two operators in QCD are extremely well known. And so they're characterized by a spin J and a transverse spin J equals 0, 2. And so these are kind of very familiar objects, for example, in Peskin. And so you have one for quarks shown here, one for gluons, and then you have a transverse spin 2, one for gluons shown here. And so much like for this, how we took this stress energy tensor and integrated it along null infinity, you can do the same thing of integrating these operators along null infinity. And this will give us the twist two light ray operators, which can appear in our operator product expansion. And the way that one can think about this is as you take kind of two of these original energy detectors and put them together, you'll get some other operators appearing in there, which are effectively detecting either quarks or gluons, and they can be either spinning or not spinning. And so the anomalous dimensions of these operators, just in the standard renormalization group, will then determine the leading behavior of jet substructure. And so I'm not going to go through all the details, but just to show that this is kind of a very concrete thing. So essentially what one can work out is just the operator product expansion, for example, of two of these energy flow operators. It just has some coefficient which can be calculated in perturbation theory. And you get out one of these twist 2, spin 3 operators shown here. And then you can perform the renormalization group evolution on this. And so this object will determine the scaling as a function of angle of these energy correlators shown here. And then by systematically kind of then if you have more, for example, 3, you then just iteratively perform this procedure, and you always get back down onto these light ray operators with differing twists, but always, differing spins, but always these leading twist operators. And so these OJ will then completely determine the scaling of an arbitrary endpoint correlator. And so just as a little aside for interpreting some of the plots later, so we will always measure these correlators inside high energy jets at the LHC. So for example, shown like this. And so although I won't discuss all the details of how one actually calculates them, including the jet algorithm, the basic idea is that at very small angles, you'll still get a completely universal behavior. But of course, as you move these to be bigger, eventually you'll hit the side of the jets, and then you'll get a non-universal behavior. And you'll see that very clearly in the plots, that there'll be a kind of sharp break where these things just move outside of the jet and then no longer really make sense. And so that's just something to keep in mind. And it's just a kind of artifact that at the LHC, you need to use jet algorithms to get high energy jets. Okay, so the first thing that one can do is to study this most basic 2-point correlator of energy flow operators. And so this is a kind of illustration here of the calculation compared with this real CMS open data. And so first of all, you can see this kind of very nice scaling behavior. And so on this side, you're outside the jet, and this side you become non-perturbative, as I'll discuss later. But you can see this kind of beautiful scaling behavior. And so the thing that's quite remarkable for me is I think this is kind of a beautiful illustration of the universality of the OPE limit in quantum field theory and the EFT philosophy. And so in particular, people, when they discuss jet substructure, may have heard that you have to do these procedures like pruning, trimming, grooming to kind of remove all these excess things at the LHC. And so in this calculation, none of that was done in any way. And so this is just a real calculation of this in the complete, extremely complex environment of the LHC. And you still, because of just the universality of the operator product expansion limit in QFT, you get out this beautiful scaling behavior independent of all the extra stuff that's going on. And so I think that's kind of a really nice, or understanding how the field theory works kind of tells you what you want to actually look at and where the universal behavior is. And so this is kind of very nice because we can now kind of answer this question by Polchinski in the affirmative, that you do see this kind of beautiful scaling behavior. And the kind of real, I think, advance of this Maldaceno-Hoffman paper was to really understand the proper field theoretic framework for understanding jet substructure and how to relate these Lorentzian observables to the underlying data, in particular the anomalous dimensions of the theory. And in particular, they really kind of showed what questions that one should ask. And the way of determining this is to really understand the underlying structure of the field theory. And once you do this, you just get out these kind of beautiful, beautiful scaling behaviors without any of these additional algorithms which have long been used at the LHC. But so the LHC data set actually allows us to go much even further than was thought by these people. And so in particular, as I mentioned, if you study higher point correlators, so for example, a 5-point correlator, you can iteratively perform the operator product expansion and you get out one of these OJ. And so in particular for 5 points, you'll get O6. And so you can then just study the scaling behavior of an arbitrarily complicated correlator. And so what I'll show in a second, to isolate this anomalous scaling behavior, it's very convenient to take the ratio to the 2-point correlator. So one can study this particular ratio shown here of the scaling behavior of an n-point correlator over a 2-point correlator. And so remarkably in the LHC data set, one can just do this all the way up. So we've done it so far up to 10-point correlators. So this is quite remarkable that this is possible. And so this is a plot of this ratio as a function of, so this is this angle between the correlators, theta, again, of this particular ratio shown here. And so the fact that these have a non-vanishing slope shows that these different light ray operators scale at the quantum level in a different way. And so in particular, you can see that this slope in this region shown here, where you're under perturbative control, gets steeper and steeper and steeper as you go to higher and higher point correlators. And this is a very basic feature of all quantum field theories, namely that these anomalous dimensions are convex as a function of this spin. And so this is something that one can just see kind of beautifully by eye, and you can really probe the kind of Lorentzian scaling behavior of these operators at the quantum level, which I think is quite remarkable. And so just like before, one can actually do a very nice quantitative test. So this is with Kyle Lee and Bianca using earlier factorization theorems derived here. And so one can actually kind of quantitatively test the structure of these anomalous scalings and, for example, probe the spectrum of twist to anomalous dimensions and the strong coupling constant in QCD. And so you can see this here for the 3-point, 4-point, 5-point, and 6-point. And it's really kind of probing in a detailed way these scaling behaviors of these observables within jets, which I think is extremely neat. Okay, so scaling behavior is kind of the most basic thing that one wants to look for in jets. But of course, one often wants to go beyond that and to measure higher point correlation functions, which tell you more detailed aspects of how, in this case, the quarks and gluons interact. And this is very similar to in condensed matter systems or in the cosmic microwave background, where the higher point correlation functions really tell you more detailed features about the underlying theory as opposed to just the scaling behavior. Oops, sorry. So this just froze for a second. Okay. And so these multi-point correlators, as I just said, they probe in a very nice way the interactions of these quarks and gluons. And the first non-trivial shape dependence is at 3 points. And so here I'll kind of show this in a triangle where you have 1 point at 0, 1 point at 1, and 1 point at some complex value z. And so though I won't unfortunately have time to highlight it, the ability to measure these inside the LHC jets relies on the use of tracking information. And so we have a nice formalism developed by some of these people here, which allows us to perform first principles calculations incorporating tracks. And so that will be kind of swept under the rug, but that's what kind of really allows this to be done at a very precision level. And so just to show a little bit, although I won't go into too much detail, why these things are very nice to calculate theoretically, I'll just kind of show what they look like in perturbation theory. And so if you actually try and compute one of these correlation functions in perturbation theory, the way that one does this is you're kind of integrating over the energy fractions that go through your different detectors, but with the angles between the calorimeter cells completely fixed. And so in particular, you'll get some integral like this, where these omegas are the energy fractions, and they're constrained just by energy conservation. And then you have some matrix element, which in this case is the, for example, 1 to 3 splitting function for a quark into 3 partons. And so I'm not going to do the actual calculation, but I just want to show for a kind of toy illustration, if you just have this Mandelstam, the type of integral that you get. And so in particular, if you just write out this Mandelstam in terms of these energy fractions and these complex coordinates, you get an integral of this form shown here. And so if one has played a little bit with Feynman integrals, you'll immediately recognize this as a Feynman parameter integral, where these are interpreted as the Feynman parameter, and these zij's, which are the distances between the calorimeters, are the standard dual coordinates. And so what this allows one to do is to very easily map these integrals for this energy correlator to a kind of dual Feynman graph geometry. And the structure of these integrals is extremely well understood. And one can then just essentially read off the answer. And so, for example, for this particular piece here, this is just a toy example, you get this 3-mass triangle integral shown here. And so if you actually kind of go through, for the particular case of the 3-point correlator, which I discussed earlier, and I'll show it just here for n equals 4 for simplicity, you get out this extremely simple answer shown here, where this u and v are written in terms of this z, which I showed before, are these standard variables from the study of correlation functions. And so this gives a very, very kind of beautiful answer if one is used to this type of thing. And in particular, it's expressed in terms of these polylogarithmic functions, which are quite familiar from the study of amplitudes. And so I should say the real QCD result is a little bit more complicated, but it involves the same functions and just has more complicated polynomials. And so this really allows us to start computing these higher point correlation functions in the real LHC environment, and they have a very beautiful structure. And so what's even kind of more beautiful is one can actually just go out and directly measure these multi-point correlation functions of light ray operators in LHC data. And so this is really a correlation function living on the detector at infinity. And I think to my knowledge, this is the first ever measurement of a correlation function of these light ray operators in any quantum field theory period. And so just to describe a little bit what's being plotted here, though it's a little, if you haven't spent some time looking at it, it's a little confusing. So this triangle lives in this particular circular region shown here. And so to make it possible to look at it or to bin experimentally, one can perform a kind of mapping where you blow up this particular region shown here into a line. And so you can think of this phi as an angular coordinate about this OPE limit, and this C as describing the approach to the OP limit. So for example, up in this corner is an equilateral triangle. And as I move down to here, I'm kind of collapsing the middle of the triangle down. And so down here, it's a fully flattened triangle. And so this is kind of on the left, a theory calculation, and then here an actual measurement of the structure of this correlation function. And so if you want some entertainment, Wajing made a very nice YouTube video, which is shown here, which plots this two-dimensional correlation function as a function of the overall scale of the triangle as you kind of zoom in. And so the thing that's quite fascinating in QCD is that if you're probing this at very at larger angles where you have perturbative quarks and gluons, you see this nice structure coming from the detailed interactions of quarks and gluons. And then at some scale where you hit the hadronization transition, this just washes out and the final hadrons are completely uncorrelated. And so you just get essentially noise. And so you can actually see kind of a video of the transition between quarks and gluons and confined hadrons. And there's a nice kind of music video of this, which it's not quite the same if I played on my iPad. And so one should watch it. It's kind of, or it's quite fun. Okay. And so why is this so neat compared to, for example, other jet substructure observables that you can measure? And so the thing that I think is really quite beautiful is that this is an honest to goodness correlation function which lives on the celestial sphere. And so it's a real physical observable that experimentalists will measure, but it actually has in it all the nice theoretical properties that one would want of a true correlation function. And so this is very different from than, for example, just standard jet cross sections, where the kind of underlying amplitudes are, of course, very beautiful. But then when you have to put them into these actual jet cross sections, it's kind of very ugly. Whereas here, you really get in these actual physical observables, this beautiful theoretical structure living on your detector. And so just to highlight one kind of simple feature of this nicer structure, I'll show how one can decompose these correlation functions into partial waves, which are called celestial blocks. And so this is very similar to, for example, if you have a 2-to-2 scattering, you can decompose it into partial waves, which have the particular SO3 symmetry and their quantum numbers. And so here, this correlator is a function of Z and Z bar. And so you can do a similar decomposition into the appropriate partial waves of the Lorentz group, which live on your detector at infinity. And so the way that one derives these is by studying the action of the Lorentz group on your celestial sphere. So in particular, the symmetries that we'll be most interested in are boosting along the direction of the jet. And so this will have a particular quantum number, which is called the celestial dimension. And then you'll have rotations about this direction of the jet, which will give something called the transverse spin. And so here I'll mostly focus on it in this jet substructure limit, where these are very kind of transparent. And so in particular, these correlators can be thought of as living on the plane transverse to the jet. And so this boosting along n is really just dilatations of this plane, and then you can rotate it using this transverse spin. And so these are just the quantum numbers which characterize how that behaves. And so, although I won't go into the kind of technical details, one can derive the appropriate partial waves, much like you do in the case of 2-to-2 scattering, by just writing down the appropriate quadratic Casimir. So in this case, it's the Casimir of the Lorentz group, and then solving for its eigenvalue, or solving the eigenvalue equation to determine the partial waves. And so it doesn't matter exactly their particular structure. There's some product of hypergeometric functions. And so just if you're familiar, you may have guessed from this particular illustration here that these should just be the standard global 2D conformal blocks. And that is indeed the case. And so what that gives is that one can just decompose this correlation function into these particular sets of partial waves. And so one thing which is kind of really nice is that this is a kind of extremely concrete thing and can just be thought of as a kind of Fourier analysis for these energy patterns on your detector. And so this is just for fun, a kind of plot of these particular partial waves for some different quantum numbers. And so it's using these same coordinates as before. And so, for example, you can see at higher transverse spin here, you have this kind of oscillatory behavior as a function of this angular coordinate. And so the idea is that one can then just kind of add a few of these together to build up the answer. And so this is exactly how one analyzes higher point correlation functions, for example, in condensed matter systems, is that you understand the OPE data and then you just add a few of these together, since these are completely fixed by the symmetry structures, which in this case is the Lorentzian symmetry of the Lorentz group. And so just to see how this works, so it's a little hard to look at in these 2D plots. And so in the top, this is just a slice at a fixed value of this C, so through, for example, this. And so you can see the full calculation, which I showed earlier in black, compared with Pythia, which in this case is just a filler for data. And then the expansion in the celestial block at twist 2, shown here, which is the kind of leading twist. And then if you add in the twist 4 data and the associated twist 4 partial waves. And so you can see that this very rapidly converges to the full result. And so this is extremely kind of exciting in that it allows one to start incorporating these kind of symmetry-based techniques, which are so familiar in conformal field theory, but into real world jet substructure. And in particular, this is literally the pattern that you see on the detector. And the hope is that as this operator product expansion is better understood, one can use it to compute, for example, more complicated correlation functions that you cannot yet do completely in perturbation theory. And so though I won't kind of go into it in too much detail, I just wanted to highlight that there's a lot of hope that many of the other techniques which have been developed in the context of, in particular, the conformal bootstrap, can also be used to study these higher point correlation functions of light ray operators. And so, for example, everyone has probably seen this kind of very famous conformal bootstrap kind of little schematic equation shown here, which just says that you have to have consistency between performing your operator product expansion in 2 different channels, and this constrains the structure of the theory. And so the thing that's kind of very nice is that you can really just do this at the level of these light ray operators, but in terms of perturbative diagrams. And so in particular, as you, for example, perform the OPE of 2 of these, you squeeze onto some particular operator, in this case, just a gluon operator shown here, and that has to be reproduced by the operator product expansion in the other channel shown here. And so it's reproduced by an infinite set of operators. And so this crossing symmetry allows one to start playing some of the same games which are played in the study of of correlation functions of local operators. And in particular, in these papers shown here, we kind of studied this in the large spin limit. And the thing that's quite exciting is this is kind of something which is also of interest to the conformal field theory community. So I just took this thing here from a recent SNOMES review. And in particular, that one really wants to understand the non-perturbative structure of these Lorentzian observables in conformal field theory, which is just a fancy way of saying one wants to understand jets. And it's quite nice, I think, in particular, that some of these objects, for example, this crossing symmetry, shown here for these light ray operators, this really came out of performing these explicit calculations of these jet substructure observables. And so this is something where there can be a kind of very nice interplay between QCD at the LHC and conformal field theory. And ideally, there's kind of connections going both ways, that we have very sophisticated perturbative techniques, and this can kind of help understand better these Lorentzian dynamics of conformal field theories. And so it's a very nice overlap. Okay, so now just very briefly, as I go to the end, I just want to highlight 2 kind of other interesting things which one can do with these correlators. And so the first is to at least experimentally study and see by eye this hadronization transition. So as everyone knows, real world QCD is extremely complicated, and in particular, it's not a conformal field theory. And so at some scale, which is shown here, jets exhibit a transition from weakly coupled quarks and gluons, where one can perform these first principles calculations, to these freely propagating hadrons. So at some scale, so these quarks and gluons interact, and then they start propagating out and they just flow into your detector. And so most jet observables, you cannot see by eye the confinement transition, or I've never seen one where you could kind of really just see this behavior by eye. And so the way that one will actually be able to do it, even though it occurs at extremely fast timescales, is that you can essentially map the time evolution onto this angular evolution. And so if you have extremely good angular resolution in your detector, we'll really be able to see, for instance, that these hadrons are propagating freely out into the detector. And so since we have this very sharp confinement transition in the middle, we really expect to see just extremely clearly by eye two qualitatively different regimes in a correlation function measured at the LHC. And so if you plot this over an extremely wide range, so this is logarithmic in this angle, which at colliders is called R, you can see very clearly that QCD exactly interpolates between two behaviors. So I have so far mostly focused on this region where you can perform perturbative calculations in terms of quarks and gluons. But you see very clearly by eye the sharp transition as you enter this non-perturbative regime. And then if you work out in here, you actually see a perfect power law scaling, which is associated with uniformly distributed hadrons. So if you just compute these correlators on a uniform distribution that is not interacting, you get exactly this power law shown here. And so you can really kind of, if you didn't know QCD confined, you could just see from this plot extremely beautifully the structure of the interactions and how they evolve as a function of scale. And this, I think, is also kind of a beautiful illustration of asymptotic freedom. And it's kind of different than the way that one normally does it by changing the collider energy. Here you have a fixed energy and you change the angular scale. And so it allows you to kind of sweep out a huge dynamical range of scales using jets of a fixed energy. And so I think this is a kind of neat probe of the confinement transition. And hopefully this can be measured, for example, in more detail and maybe lead to some understandings of what's actually going on there. And so in the last couple minutes, I don't want to go over, I'll just very briefly mention how one can extend this beyond just massless quarks and gluons to use it to probe the appearance of other particles, for example, the top quark appearing inside jets. And so the top quark is, of course, one of the most important parameters of the standard model. So it determines electroweak vacuum stability, electroweak fits, etc. And so one thing which is, or one issue with the top quark is that because it interacts strongly, one of the leading uncertainties is that it's actually not understood what exactly one is measuring in experiments. And so this is often kind of indicated by the fact that what one is measuring is some Monte Carlo parameter. And so one way of overcoming this is to have very simple observables which have a top mass sensitivity, but where you can compute them from first principles field theory and really understand every aspect of it. And then your top mass is a field theoretic parameter. And so if you look at a real top event, for example, here at CMS, you see, or the kind of characteristic thing is that it decays into these three sprays coming from the hard three-body decay of the top. And so if one is thinking in this language of these energy correlators, the kind of natural way of going about it and the simplest observable is just to look at this three-particle correlator. And so that's a very simple field theoretic object. It's just one level beyond these two-point correlators. And so I think it's essentially the simplest thing which captures the behavior of the top quark. And so unlike these beautiful power laws, which I showed before, where there's no intrinsic scale, once you have an actual intrinsic scale, these massive particles, even if they exist for however long the top quark exists, they will imprint their short-lived existence into this particular characteristic scale appearing in your detector. And so this is just a plot shown here of this three-point correlator as a function of this shape. So again, it's looking at the scaling behavior. But now instead of a power law, you see a very clear bump, which depends on the particular mass of the top quark. And so you can see very clearly, it just kind of, you're able to read off some characteristic scale associated with this essentially just kinematical features of this decay. And so because of the nice theoretical understanding of these observables, one is kind of optimistic for precision top mass extraction at the LHC from jet substructure. And I think this motivates further understanding of these correlation functions for their interplay with standard model measurements. And so just to conclude, so one thing which I hopefully convinced you of is that jet substructure essentially provides a physical realization of this operator product expansion limit between light ray operators. And so by phrasing it in this way or formulating it in this way, it builds kind of a direct bridge between a lot of these recent field theory advances and real world QCD phenomenology. And at the LHC, because of the remarkable energies and angular resolution, one can actually measure the shapes, and scaling behavior of these multi-point energy correlators and really just see by eye that all these basic features, such as the operator product expansion and these symmetry structures, are really obeyed. And I think this is kind of a really neat avenue to measure these light or correlation functions of light ray operators, which is something that had not previously been done in quantum field theory. And so finally, there's a lot of recent progress coming from a whole bunch of different directions to try and better understand the structure of these matrix elements of light ray operators. And so hopefully this will have a lot more impact on the way in which one understands QCD at colliders such as the LHC. So thank you.